Hey everyone, this is part 2 of the application of differentiation video. So this is section 4, application of differentiation, part 2. And here we're going to talk about the 3 word problems that are in this section, right? First I'll start with problem 27. So this one says that we have a farmer that's enclosing two side-by-side pens next to a river. So again, I'm going to draw my picture. Let's pretend that this right here is a river, and I'm assuming that this is a rectangular kind of thing. So we have two side-by-side pens, just like that. I don't know if they're going to be equal or not, they just happen to be in my picture. And I want each pen to contain an area of 150 square meters. And we want the minimum amount of fence that to build this. So let's call this X, let's call this Y. So the total area X times Y has to be exactly the sum of that, which is 300 square meters, right? So that's an equation relating the variables X and Y. And now I want to minimize the amount of fence. So the amount of fence, let's call that capital F. That's going to be, well, we have 1, 2, 3y, because we have 3 sides of this length, and we have 2 x's. Not 2 x's, 2 times x over 2, because this would be x over 2, and this would be this is an equation
of 2 variables. I want to turn it into an equation of a single variable so that I can solve using calculus. So I'm going to use my top equation, which is my constraint equation, to solve for y in terms of x. And what that gives me is a function of a single variable now, f of x, which is 3y, so 3 times 300, which is 900 over x plus x, right? And I wanna minimize this. So what is the minimum amount of fence needed? Let's figure this out. So I have to take the derivative, f prime of x, that's minus 900 over x squared plus 1. Notice I have, of course, x equals 0 is one of the critical points, but that's irrelevant because in terms of the geometry of the picture, that means this is just flat. Alright, so it doesn't make any sense. And basically what I'm trying to solve is, when is 900 over x squared equal to 1, right? That means x squared is equal to 900. So now I just take square roots, right? So I get that x is going to be, of course, plus or minus 30, but we're only going to take the positive root. So this is the critical point. And now if I plug this into the original, the minimum amount of fence is going to be f of 30. And the way you can see that, okay, why is that a minimum? Simply because, let's think, what's going on here? 1 second. I'm looking at the derivative. We'll talk about it in a second, right? So f of 30, and that's going to be 900 over 30 plus 30, right? So this should be 60 meters of fence. Okay, now the question is, why is this a minimum? Well, let's take a look at a derivative. If I plug in something that's slightly bigger than 30 into capital F prime, then this quantity is going to be less than 1, right? Because I'm going to have something larger than 30 squared, right? So it's not something, the denominator is going to be larger than
900. So I'm going to subtract from 1 something that's smaller than 1. So this is going to be positive, and of course if I do it the other way around, if I plug in something less than 30, then this term right here is going to be greater than 1. When I add 1, this is negative,
so the function has to go from decreasing to increasing, and that is why this is a minimum. So that's problem 27. Let's move on to problem 28, which is a bit more complicated. So let's see, what do we have? We have a hallway for problem 28, and I'm going to copy the drawing here, and there's a narrower part for the hallway and there's a wider part for the hallway, right? The narrower part is 6, I guess, feet wide. The wider part is 9 feet wide. And the question is, what is the length of the steel pipe? How long can the steel pipe be if I try to go around the corner? So in the picture given to us in the problem, there's a label for this angle theta, which means we should introduce some kind of right triangles here. And the way I do this here, a side of 9 here, because that's the width of the two hallways. And because here I have two vertical parallel lines cut by a transversal, which is the orange line, then this angle is also theta. So right away, if I label this to be L1 and L2, I can start writing down some equations, right? And I'll do them over here. I have L, the total length of the pipe, is going to be the sum L1 plus L2. And let's see, in this right triangle, in the bigger of the two right triangles, I have opposite over hypotenuse, so sine of theta is going to be 9 over L1, which allows me to solve for L1. L1 is going to be 9 over sine of theta. And for the other thing, I have cosine of theta for the other triangle is going to be 6 over L2, which allows me to solve for L2 in terms of theta. So then I get that L2 is 6 divided by cosine of theta. And now I can write an equation for the total length of the pipe strictly in terms of the angle. So L of theta, which is where L is the total length of the orange line, is going to be L1 plus L2, so it's 9 over sine of theta plus 6 over cosine of theta. Okay, so this is the equation that we're working with, and I want to, of course, figure out the extreme values for this. Now, the longest pipe can actually, if I were to draw the following picture, the longest pipe would happen when theta is very close to 90 degrees, so the pipe would be infinitely long, right? And the same is true for the smaller pipe. When theta is very small, the pipe can be infinitely long, but it won't make it around the corner. So in fact, what I want to do is I want to find the smallest pipe, which is what this line will be. So I want to minimize this function. Okay? Of course, I have to take a derivative, so L prime of theta is going to be, okay, this is sine to the minus 1, so what I can do is I can say it's negative 9 over sine squared theta times cosine theta. And now I have 6 over cosine squared times negative sine of theta. So this becomes a plus, because I get an extra minus sign from applying the power rule. Notice this is undefined, like I was mentioning. When theta is pi over 2,
right? Because I get 0 of that, and when theta is also pi, and that corresponds to an infinitely long pipe. But we're not interested in that extreme value, so we can ignore those critical points, and I can just look at when this is 0. So now the thing that I'm going to do is I'm going to multiply both sides by sine of theta. So I end up with minus 9 divided by, okay, if I multiply by sine, one of the signs cancel, so I have cosine over sine. So I'm just going to divide by tangent, right? Take the reciprocal, plus 6, and now this becomes tangent squared theta equals 0. So this is the equation now that I'm trying to solve. And what I'm going to do is I'm going to let x be equal to tangent theta. So I'm trying to solve basically 6x squared equals 9 over x. Multiply everything by x, so I have 6x cubed equals 9, or x cubed equals 9 over 6, which is 3/2, which means x should be the cubic root of 3/2. But x is tangent of theta, so that tells me that theta is the arctangent of this value. And of course this is not some particularly nice value, but we can of course approximate it using a calculator, right? So then you take this theta value, you plug it into the original function here, and that gives you the maximum length of pipe, and I believe that was something like, it was 21 point something, right? So once you do the calculation, L is approximately 21 feet once you plug this value in for theta. So that's problem 28. And now for probably the most difficult question on this review is problem 29. And for this question, let's see, what do we have? We have two vertical poles sitting on the ground, one of them being taller than the other, and they are connected by a line just like that. Okay, so let's start labeling things. This is the little height, the height of the little pole. This is big H, the height of the large pole, and this right here, this line here, is the string. So let me use a little bit of color, right? I already drew it in pencil, so it's going to be kind of hard to see, but you get the point. Theta 2.
I'm going to call this distance right here x. I'm going to call this whole thing, the distance between the poles, d, which is going to be constant, just like the h's. And I'm going to call this distance right here x, d minus x. I also need to label the length of my string, and the string is comprised of two pieces, little L1 and little L2. So now we get to use these right triangles, and I get the following equation. I get that L1 is, using just the Pythagorean theorem, is going to be the square root of h squared plus x squared, and L2 is going to be the square root of capital H squared plus d minus x quantity squared. Okay, that's just applying the Pythagorean theorem to these right triangles. So the thing that I'm interested in is the actual length of the string, which notice depends on x. So that's going to be L1 of x plus L2 of x, which is these two functions here. So I just get square root of little h squared plus x squared plus square root of capital H squared plus
d minus x squared. Okay, so this is the function that we are now interested in minimizing because we want the least amount of string. Okay, excellent. What do we have? Well, I have to take the derivative, so L prime of x, that's going to be 1 over twice the root for the first term. Let me just change the lead in my pencil real quick. There we go. So twice the root a squared plus x squared times 2x from chain rule plus 1 over twice the root of the bigger term times 2 times d minus x times negative 1. Okay, so this is equal, once I simplify some stuff, this is equal to x over the square root h squared plus x squared plus, rather minus d minus x over the square root h squared plus d minus x quantity squared. Okay, but I know that L1 and L2 are the denominators of this expression, so let's go ahead and replace that in. I have L prime of x is equal to x divided by L1 plus d minus x divided by L2, right? So this is what I have here, and now I go back to my drawing. X divided by L1 is cosine of theta 1, and d minus x divided by L2 is cosine of the second angle, theta 2, right? So that means L prime is now in terms of the angles, in terms of theta, it's going to be cosine of theta 1 minus cosine of theta 2, and of course I want to set this equal to 0. Now when is this equal to 0? This happens whenever theta 1 equals theta 2. Okay, so that's the key here, is that the derivative of the length of the string that I'm using is going to be equal to 0 precisely when the two angles are equal to each other, right? Now the question is, okay, so this is going to happen for some x inside the interval, and the range for x is 0 to d, and the question is this a minimum? And of course the answer is going to be, well, I just take L prime of the endpoints, so L prime of 0 is going to be, let's see, it's going to be negative d over square root of capital H squared plus d squared. These are all distances, so this is less than 0. And L prime of d, the other endpoint of the interval, is going to be d divided by square root little h squared plus d squared when I plug in d for x, and that is greater than 0. So this implies that this is indeed a minimum of my function L. So that's it for the applications of the differentiation section, and I'll see you in the next video where I start talking about integrals.